Okay, so this is what we've got. We've got, as we go from point 1 to point 2, we had two ways. We could go along this isotherm, or we can go constant P and constant volume, and we get two different works. Well, the first law of thermodynamics says that the change in internal energy that we get going from 1 to 2 is equal to the heat added minus the work done. Okay, and so the missing piece here to get everything to match back up is, of course, our heat. So if we look at this, then our heat, just to get the signs right, Q greater than 0 means that it's added. The temperature increase, well, the temperature increases generally when we add heat, right? We've also got situations where phase change can happen, or we could add heat and it could all go into work. The temperature could just stay the same. If we have heat less than 0, that would be when it's lost or removed, okay? And similarly, just so we have a consistent thing, work is greater than 0 when it's work done by the gas, and work is less than 0 when it's done on the gas. Okay, so as I said, we could have a situation, and that's what we have here. If the temperature is constant, well, the change in internal energy as we went from 1 to 2, not only the same, but it's 0. So let's look at this. From 1 to 2, the temperature change is equal to 0 because change in internal energy would be internal energy 2 minus internal energy 1, and that would be 3/2 kb delta T, and our delta T is 0, so we have no change in internal energy. So along this constant T, all of the heat must be equal to the work because we have delta E equals 0. This is the first law of thermodynamics. It says that the work went into not changing the temperature, it went into heat. So that says the heat for constant temperature process is equal to nRT natural log of V2 over V1. In other words, heat got added into the system. It's positive. This is a positive value. If V2 is bigger than V1, this is positive. Heat was added to the system, and there was no temperature change. Look at that, okay? When we were talking about solids and liquids, the only time we had heat added and we didn't have a temperature change was with that phase transition, as I said just a little bit ago. But for gases, we can have a situation where the temperature gets held constant and we're not changing the internal energy, but we can have heat added into the system. And all of that heat goes into work. Okay? So that's a nice way to connect heat into some physical work that gets done. Now, in this second instance, right, we have a change in internal energy because this is a higher temperature that's higher. Higher. And we can figure out both the change in internal energy and that's created by both the heat and the work here. Okay, and so we'll look at that for constant pressure processes. For a constant volume process, notice in step B here, we have no work done. So in this, I'm running out of colors here. All right, so in our constant V setup, the work is equal to 0, so then all of the heat change goes into a change in internal energy. In this case, from here to here, the internal energy is negative right? Because the temperature goes from a high to a low temperature. So this change in internal energy, the final energy is lower than the initial. This is negative. So Q is negative. So heat is actually lost in this situation as we go from a high pressure to a low, a high temperature to a low temperature at the same volume, okay? And in fact, we can say that our change in internal energy is equal to, just looking at that, 3/2 in KB delta T is equal to our Q. Okay, so this tells us how much heat goes into a change in temperature, or how much heat is lost when the temperature changes. So this is very similar to what we saw when we were looking at specific heat things, that this tells us how, based on how many particles we have, and this constant would tell us how the temperature changes. Recap a little bit before we go to the constant pressure. At constant temperature, which is called isothermal, an isothermal process, the change in internal energy is 0 because there is no delta T, right? Change in internal energy is 3/2 in KB delta T. So if delta T is 0, that's 0. Using the first law of thermodynamics, if that's 0, then work must equal Q. So work equals Q. In other words, any work done comes from the heat, or vice versa. Any of the heat that goes into the system goes into work. When you have constant volume, there's no work done. So if work is equal to 0, then this change in internal energy is the way we get the heat. So as this heat that's transferred into the system causes a change in temperature. Okay, with a constant pressure process, we've got sort of both things going on, right? We've got Q and we've got work and change in internal energy. So here, the change in internal energy is equal to 3/2 KB delta T, let's say T2 minus T1, because we're going from 1 to 2. The work done is equal to P, V2 minus V1, but I can actually rewrite this. I can write this as my pressure is constant. I'll rewrite it here. P work is pressure V2 minus pressure V1. If I use our ideal gas law, that is PV equals nRT. This is 0.1 and this is 0.2. Then pressure, the pressure is constant, times V1 is just going to be nRT1, or I can also use PV equals nKBT, which probably, yeah, I want to use it in that form. So, or, well, let me do this. nRT2 minus, that's the work done, or I can write it in this form, KB T2 minus T1. T2 minus T1. Okay, I can take this and I can take this and put it in the first law of thermodynamics, which is just conservation of energy again, because it's saying the change in internal energy depends on how much work is done, how much heat is put into the system, less however much work the gas did. We can put these two pieces in and solve for our Q. Okay, putting this all into this equation for P constant, I'm going to rewrite this equation right here and say Q is equal to delta E, bringing the W over, plus work. And then I'm just going to plug this for right here and this equation for right here, and my heat is going to equal 3/2 in K, oops, there's a KB, sorry, KB delta T plus in KB delta T, so that's a 2 over 2, so my heat is equal to 5/2 in KB delta T. So this is usually called my heat for a constant pressure process, and this is usually called my heat for a constant volume process. So you see in your book the heat associated with a constant pressure process versus a constant volume process. And the reason it takes for the, you can see a different sort of heat capacity here, right? This is related proportional to your heat capacity, is going to be because this process, some of the heat goes into not only internal energy, but also to work done by the gas. So you put some heat into the system and you change the temperature, but you also end up generating work. The gas expands as well over here. In this situation, you put heat in, the volume is fixed. So this is like a fixed container, and you increase, you have heat that goes into it. It all goes into changing the temperature. So notice that these, the heat and the work, depend on the process, depend on how we do it, whether it's constant temperature, constant volume, constant pressure, but the change in internal energy only depends on your endpoints. So some vocabulary, this is called an isobaric, and this is called an isochoric or isovolumetric, if you like. That's just so if you're looking things up, you can find them very quickly, okay? And it's useful to keep these different thermodynamic processes separate. And the way I like to do it is to try to think about, well, what does the graph look like? I mean, you can create this kind of table for yourself, but think about what does a graph look like? Because this work is the area under the curve on a PV diagram. So if your PV diagram, if it looks like this, you can calculate the area under the curve. That would be constant. If it looks like this, there's no area under the curve. That's a constant V, right? Because the V stayed the same. Or if it's like this, then we're possibly, hopefully, on an isotherm where we have constant temperature, okay? Now, to get from one point to another, you don't have to follow any one of these processes. But these are the ones that are easy to calculate, okay? So that's why we spend some time giving them names and identifying them. But it's true that you don't have to, you can get from here to here along a straight line like that, where the pressure, volume, and temperature are all changing. It's just a little more complicated to write some of these equations for it.